up, the size of the detector in comparison with what has been done before. And what is here is a big sphere which is filled in by 1,000 tons of mineral oil, and that worked like a scintillator detector. And again, they looked inverse beta decay and detected essentially these positrons produced in this detector. Now, this is another type of reactor experiments. By the way, Kamlan detector, which is in Japan, it still works, but it now looked for beta decay or double beta decay, because essentially atomic reactors do not work in Japan anymore after the disaster, and Fukushima disaster. So this is Daya Bay experiment, which runs now, and you see here 3 experimental holes, and this is EH1, EH2, and then a remoted one, EH3, and these blobs of pink color are atomic reactor complexes. And so there are 6 reactors, and each has this huge power, 2.9 thermal power, 2.9 gigawatt. So on the left-hand side up, you see the remote reactor. So that's one EH3, which is further from a line of atomic reactors. And so there are 4 detectors even inside. And so they detect, again, this inverse beta decay. And they're looking for oscillations. So they have actually discovered oscillations. I will discuss this later. So this is the result, which I'll probably discuss later. This is another reactor experiment. And you see here these cupoles, which are under atomic reactors. And they have detected close to the reactors and further detected a remote one. So this is another one, double CHOOZ, probably I will not comment much. So you see here, again, reactors, 2 reactors, and detector at the distance about 1 kilometer. This is July's future experiment, which I was probably mentioned, and that experiment is meant to detect to establish what is the mass hierarchy of neutrinos. And you see the size already now here is 20 kiloton of scintillator in this detector. And so they will measure the spectrum of positrons from inverse beta decay. Now Cherenkov radiation, and you see here Pavel Cherenkov, and you see here upper part of atomic reactor, which is covered by water, and you see the shining blue light. It's not it's not a made picture. This is what is in reality, and this blue light is due to Cherenkov radiation. So you see also blue light here. There's also part of the atomic reactor. Here is the picture. It's another application of Cherenkov light. I don't know if I think that it should be somewhere pointed out. So particle moves in this direction. So for instance, this is neutrino, red. It interacts and produces, say, muon. So muon moves in water. This is inside the Earth. It moves in water. And you see these shock waves, what I was saying. So that's Cherenkov light. And this is kind of the front of this coherent light. Again, I'm asking, please come in time. I don't know what's wrong. Why you cannot come in time? So we are starting exactly at 11, please. And you see here, these are chains of photomultipliers. This is how IceCube operates. There are strings, and optical modules are attached to these strings. They are as long as 1 kilometer length, and you see what they are detecting. They are detecting this Cherenkov light produced by particle moving inside in the water, or this is in ice. So here you see inner part of Super Kamiokande detector, which is operating now. And you see here people staying here, they're cleaning things, and it was some disaster some years ago because one of these photomultipliers was broken, and then it was shock wave inside after this breaking, and many other photomultipliers were destroyed, and so they repaired the detector. Many interesting results have been obtained here. So here you see typical Cherenkov rings on the walls of this detector, and the colors here means time. So they also can detect when the pulse is arriving, or Cherenkov signal arriving at the given photomultiplier. So these points are photomultipliers, and you see here is upper part of this Super Kamiokande detector. So these rings are really big. So it's 10 meters of radius. It's not a joke. Now, what you see here, this is event where there are 3 even particles in final state, several particles in final state. So they produce Cherenkov light. So here is how they identify the type of the particle. You see the upper picture corresponds to muon, neutrino and muon. You see the track, and you see this muon which is produced and then absorbed, and you see these cones, 2 cones in which light propagates. And for muon you see very sharp outer parts of this ring, because there is no scattering, multiple scattering. As for electron, here you see the electron actually moves and they change the direction, and also there are some other electrons here, and you have very diffuse ring. And so this is the way they distinguish electron and muon in the detector, which is extremely important. Now, cosmic rays, here you see Victor Hess, and the real photo when he was flying using balloon, and then you see his balloon, and measured radioactivity and measured discharges of electroscope. So here is a modern version. People celebrated 100th anniversary of discovery of cosmic rays, and so they produced this electroscope, also were flying, and a number of discharges increased when they went up. So here's some picture of cosmic rays. You saw already what is on the left-hand side. This is development of the air shower. And on the right-hand side, you see really the size of this phenomenon, because although this is kind of pictorial, but it reflects correctly the size. So you see here the part of the Earth, and this is the size, really huge. And you have primary particle which interact somewhere at the distance 15 kilometers from the surface, and that can be several kilometers size. So this is the spectrum on the right-hand side, and again, development of the shower. So there are a number of different types of methodics to detect cosmic rays, and some of them using also Cherenkov light and also scintillator light. You see here some telescopes. Now this is IceCube detector. You saw before some strings of this detector. Here you see Torefeld, and the size is, this is 1 kilometer, and this is 1 kilometer, essentially kilometer cube detector. It's below the surface, and upper layers serve as a shielding from backgrounds. And what you see on the right-hand side, these are 2 first events which are ascribed to cosmic neutrinos. And they have huge energies. You see, it's PeV. As TeV is what we see now in LHC, and the energies of these events are PeV, 1,000 times bigger or 100 times bigger than what typically we see at LHC, which is the biggest detector. Now, this is picture of this event. So what does it mean? This means color means time. The red where the signal appears first, and then it looks like you have some interaction in the central part, and then secondary. So what you have, this is electromagnetic interaction. So most probably this is electron neutrino. So that produces electron, and then so electron produces cascades, and then you see the signals, and those are different strings, and the difference distance between strings something like say 60 meters or so. And so you see huge size of this phenomena. You see, so that's one elementary particle originally produces this, so a single neutrino. And the size of these blobs corresponds to the signal, strength of the signal detected by a given photomultiplier. So of course from here it is difficult to identify the direction, but still they managed to identify even the direction from which particle came. For muon it is easy because you have more kind of focused track. So these are two cosmic ray events. They have even names, Ernie and Bert, you know, it's personal. So the total number of events now it's something like 60 or 70 above, say 0.3 PeVs. Okay. So sources of the cosmic rays. On the left-hand side, also here you see supernova remnants. So supernova explodes in the galaxy and it produces shock wave, and you see here shock wave propagating in the gas of the galaxy. This is much stronger phenomenon. This is jet. Remember I mentioned jet emitted from active galactic nuclei, and here probably a black hole is sitting, and so you see here the jet. And the huge amount of mass is moving in this direction with essentially relativistic velocities, close to velocity of light. Probably these are the sources of the cosmic rays, and shock waves inside these jets are accelerating cosmic rays. So this is Wilson chamber. You see the chamber and pump, which produces super cool conditions and therefore unstable, and so you can enhance effect even of small ionization. So this is famous event of positron discovery, and you see positron is coming from here, and then it crosses the plate of lead and loses some energy, and you see after crossing the lead it has bigger curvature. So that's discovery of positron. Now this is, here you see on the right hand side you see these famous tracks produced by Pine. I have shown this part. So you see the middle track is practically the same in all 4 lines, so practically the same. So pines are below, you see pines are coming and then produce muon, and then muon decays and produces electron. And Powell got a Nobel Prize for this. So not accidentally, because you know it's not only discovery, it's a discovery which led to enormous consequences. So that's actually one of the criteria. So they got this he got the Nobel Prize for this. And other authors are Alchialini and Lattice. Now, Kaun discovery, and here you see this V type of the event. You see here 2 pines, and they are coming from decay of K meson. Let's see if so that's event when K decay into muon. See, one track is K meson and then mu minus. Now, scheme of linear accelerators, you saw this. And on the left-hand side, you see slack accelerators, the upper view. Now, what else? So the scheme of accelerators here, you have acceleration, it's about 3 kilometers, this LINAC, and then storage ring, and the electrons and positrons are moving in different directions, and there is an area where they are colliding. So these are another Linux, so yet another linear accelerators, and you see these cavities with gaps between. This is synchrotron. I think it's Tevatron, not LHC. This is tunnel, and you see here is a slight turning, and you have magnets here, and in some areas there's acceleration lines. Yeah, so this is Tevatron in Fermilab, and you see upper view of ring. Somebody was in Fermilab? No? You were?
Yeah, but just visiting.
Okay, so this is building where theoreticians are sitting somewhere here. There's canteen. Now the ring is, of course, it's under the earth, but not too deep. So that's a kind of the circle. This is Tevatron, which accelerates protons and antiprotons. You see the energy, total energy in the center of mass is 1.96 TeVs, and then you see in tunnel view, this is the tunnel and the pipe where protons and antiprotons are moving. Now this is LHC, and by the way, so the length, I think this is something like 1 kilometer, right? So now this is LHC, and you see you need to go upper to see all the things. So that's kind of not what you see, but again, it's under the earth, it's something like 100 meters, 200 meters below the surface. You see here, this is pictorial view of two circles in which protons are accelerating, and this is proton-proton accelerator. So the energy of each proton now is 6.5, but next year it will be 7 TeVs. They will increase slightly the energy of proton. So this is 27 kilometers long tunnel, and you see here where is this Geneva airport. I think this is Geneva airport. Now there's mountains. And so the lake is not, I think lake is somewhere here, Geneva Lake. And you see several points where beams intersecting, and there are detectors, Atlas, CMS, and the Alice detector, and this is LHCb detector. So this is the tunnel of LHC. And you see actually in the same kind of tube you have two pipes. One is for proton moving in one direction, and another one in another direction. And here is, you see one example. I will show you more slides about different detectors. It's just example of Atlas detector, which is a toroidal LHC apparatus. And you see the size is 46 lengths, and 25 and 25 is in these perpendicular directions. So here is the Atlas under construction. By the way, the weight is 7,000 tons of this apparatus. And you see here the person which is staying inside. And so this is view of this detector, which looks like many different detectors, which is one inside another, you know, it's like for different purposes. So the most inner part is a semiconductor tracker, and then you have other detectors, and the upper detectors are usually to detect muons. So that's it for today. Questions? You should remember that our knowledge is based on these funny tracks, you know, lines. That's it. You know, then, of course, we are modeling these things. And you see how much modeling is behind, because we understand what it is. And you saw also these pictures where you see many tracks. So the experimentalists are managing to select useful tracks, because some are not useful. You need to select also useful tracks and give interpretation. Then you get what you get. So probably I will switch later. And so let us continue. There's no questions.
From these neutrinos detected at IceCube, which are the sources?
Again, we don't know.
And,
Again, we don't know. And actually, just a few days ago, it was a new publication of IceCube. They tried to see if there is some concentration of the events in certain directions. Actually, the number of these neutrinos is not big, something like 60, 70, or maybe some now it's 80. The statement is that they can still not identify.
the detectors in the South Pole,
Yes.
but it like detects all this part of the sky. They
Yes.
can distinguish like where the source come from.
Oh no, so they of course detect directions. They detect directions.
They can find direction.
And then of course people were searching for, they took different catalogs of different objects, like active galactic nuclei, quasars, Seyfert galaxies, and apparently these neutrinos have source most probably not in our galaxy, so it's at least most of them. And the flux is more or less isotropic. It doesn't look that you have really some.
Such an energetic neutrinos can just cross the Earth.
No, no, that's not true, because for these high energies, the cross section of neutrino becomes big, and they cannot cross. So they cannot cross. Remember, at low energies, we have this formula that cross section increases as energy square. This actually is valid below 1 GeV, because below mass of the proton. Remember, we derived this, we used this. However, at higher energies, cross section still increases, but it increases as energy. But still, it becomes so big that the neutrinos cannot pass through the Earth. So most of these events are just from up for this for Antarctica, or they cross some small amount of the Earth. Bottom line, they do not see clear correlation with known sources. Only one case is important, and I mentioned already before, so there is some correlation. I will discuss this later. But apparently this source, which was identified, cannot be the source of all these events, or even this type of the sources cannot produce all these neutrinos. What I wanted to add to what we have discussed before are the most important accelerators and their characteristics. So LEP, then Tevatron, and LHC. Now, colliding particles, here is E plus, E minus, here is proton, antiproton, and here is proton, proton. Now, the circumference of these colliders are 26.6 kilometers, so 27. Now, this one is 6.3 kilometers, which corresponds 1 kilometer radius. And this is again 26.6 kilometers, because it uses the same ring as LEP. Now the energy is 110 GeVs, and all they are colliders. This is 10 to the 3 GeVs each beam, and this 7, 10 to the 3. And finally, luminosity. Here it was 5, 10 to the 31. This is not integral, but luminosity in the units centimeter minus 2 seconds. Now the Tevatron has luminosity 2, 10 to the 32. And LHC, the peak luminosity now is 10 to the 34. Okay? And finally, let me give you just a little bit more information about LHC. So LHC has, at least what they had in the beginning, 2,835 bunches moving at the same time inside the ring. Each bunch has 10 to the 11 protons, and the size of the bunch, as I mentioned already, is 7.5 centimeters, and the radius is 0.016 millimeters. Now they have frequency 400 gigahertz, or megahertz, sorry. So the size of the cavities is smaller. Remember, we estimated 10 meters for 30 megahertz, and since the here frequency is bigger than the size of the cavity, it's smaller, something like meter or something. So now the time of acceleration is 1,200 seconds. Complete acceleration time. Acceleration. And acceleration proceeds in several phases. So first is some small linear, then PS ring, which accelerates, I don't remember precisely the energies, to say a few GeVs, then SPS ring. So it's like you have one ring, then another ring of acceleration, and then the particles are injected in this big LHC ring. So the duty cycle is the following. So it's like every day you repeat the same procedure. So you turn this accelerator, and then you accelerate during the time 1,200 seconds. And then during the day, the particles are moving, colliding, and you observe some events. Of course, these beams cannot live very long time because they have collisions, some scattering, and then everything is polluted. And then you need to clean your rings. And so every day they have cleaning of the rings, which means they beam dump this. So what they do is beam dump. So they have some target, and then put this and put beam of flux of the protons on this target, and so just remove it, and then next day start again the procedure. Okay. And they have very complicated, they have superconducting magnets, of course, and very sophisticated system of managing with this, because again, you need to collide this type of the beams which are moving in this 27 kilometers ring. Yeah.
I don't know if you have to put
change from the slides.
the old recording slides.
So what? Sorry.
You should.
The recorder is recording the slides still.
Oh.
Yeah.
Oh. Okay, so I'll switch. First, of course, I should switch this one, and then I will remove this one. And so we can try it. Thank you. So let's proceed further, and then our next discovery is discovery of muon neutrino. But before, I want again to give some information about how tracks of particles are observed. So we discussed already the use of phase transitions, and the idea was to have a detector in unstable situations so that even small ionization produces a visible effect. So there's another methodics of detection. Which is somehow realized in photomultipliers. So suppose we have some medium, particle crosses, produces ionization, and then we apply the field, electric field, so that electrons are moving in this direction and ions in this one. They move, collide with atoms, and produce secondary ionization. Which can be quite big. And secondary ionization is related to the primary one. If the tension of electric field is not so big, then it linearly depends on primary ionization with some coefficient which can be actually as big as 10 to the 5. So you strongly enhance the ionization signal, and then you detect here, you put here detectors, you detect the secondary ionization, and that produces big pulse. So this is used in so-called proportional counters. So you measure the secondary ionization, use this relation, and you can calibrate your experiments. You can measure this proportionality coefficient, and so then you can recover, measure what is primary ionization, and on this basis you can conclude what is the energy of particle, and also can say something about the nature of the particle. That was enormous development of this type of the technique, and one of these developments is creation by Georges Charpak, and he got Nobel Prize for this. So-called multi-wire chambers. So these are the chambers which are filled in by planes of wires which are directed in different way. So in one plane it is like this, and another plane is like this, and then it's another plane again like in the original one. And so they have opposite charge, and particles producing ionization here produce this primary ionization, and then it is enhanced and then detected by different wires. Collecting the signal from different wires, you can very precisely reconstruct the track of particle, okay? Knowing what is the signal on each of these wires. One of the very often used these days, and even in future we'll probably meet this again. Development of this type of a technique is so-called TPC, which stands for time projection chamber. So many detectors, many experiments are operating with these TPCs these days. So what is this? Schematically, you have a cylinder type, and you have detectors here and there, fine structures. So you have many detectors here. A particle again produces ionization, and you collect the secondary ionization by these counters. You can even produce here some additional enhancement of this. So why this time projection? Looking at signals in these different photomultipliers, you can see what is projection of this track on this plane, right? Measuring the time of the signal, you can identify what was direction in this Z. So how particle propagated in Z. Okay, you use projection here. And you use time of arrival, and you can reconstruct what is Z position. So that's why it's time projection chamber. And again, you can reconstruct trajectory of the particle, and also intensity of ionization, primary ionization. You see, at the same time, we have so developed methodics, but everything is reduced that we measure the track, right? Or we see what the track and what is energy loss, what is energy release in this track. And using this information, we get all what we are having now, this beautiful standard model. Everything comes actually practically from this type of events and observations. What else? Probably final comment is that we can even have a way to see the tracks, not just collecting ionization. And an invention is the following. Suppose we have really very strong electric field in our detector. And then what particle produces, it produces ionization, and then which leads to discharge, right? So if the tension, electric tension is very strong, that produces discharge. And this is the basis of work of Geiger counters. You see Geiger on one of the slides. And this type of the counters used as the triggers. Suppose you have your detector, and you make some pictures like in the early days. People did just randomly pictures of the detector, like cloud chamber. They didn't know when particle will arrive at your detector. But what you can do, you can put from outside of your detector these Geiger counters, which do the following. They have very high efficiency because energy, electric tension is very high, and so if particle passes, it's almost 100% produces the signal. You don't want to measure energy and everything like this, but what this Geiger counter gives for you, it actually warns your main system. So it says, okay, something come to your detector. And then you switch your main detector cameras or whatever you want to have, right? So then detect the signal. It's not like Anderson did, just randomly make the photos, you know. But in this case, you just save your time and everything. Just the Geiger counter automatically give the signal to main system, and it switch on and make a photo, so whatever it is. So, discharges actually can be used to visualize the track, and I will show you next time slides where you can really see these discharges. So suppose you have again particle which produce ionization, and you have strong electric field. strong electric field. So what happens is that avalanches start to form. So how discharge occurs? You have electrons which are accelerated in an electric field and produce gammas. These gammas travel and can go to quite remote points. They ionize atoms so that you have production of electrons, again, which are accelerated, produce gammas, and this process, like the avalanche, start to develop very quickly. So it starts to develop very quickly when you produce gammas which are already able to ionize your atoms. So what will happen is the following. First, avalanches start to develop just briefly after particle passes through. But then what you can do, you can switch off your tension, electric tension, or make the photon when particle passes shortly after it enters the detector. And then you will see, just even you see by eye, these avalanches around along the track. Or you do the following. So you have some trigger which tells you that, oh, particle come, and then you use very short pulse of voltage, which actually doesn't allow avalanches to develop completely, but they just started to develop, right? And you can see them. And then you do snapshot. And this is what is realized in spark chambers. This spark chamber has been used to discover muon neutrino, and you will see on the slide, which I will show you later, but the spark chamber is quite big. It's like a human size, and so the person is staying and looking at the track, as you see, just these avalanches. You see this, the sparks along the track of the particle. So now let us discuss discovery of muon neutrino. So we have already discussed some processes with muons. Like decay of pion or decay of muon itself, when we have production of neutrino, electron, and another neutrino. Pontecorvo was actually one of the first who mentioned that muon is not Yukawa particle. And so muon is analogy of electron, just heavy version of electron. And furthermore, it should be accompanied by its own neutrino. Like electron has its own neutrino. So every charged electron has its own neutrino. And then Pontecorvo was saying that there's kind of universality. I mentioned already this. So that the pairs of electron and, let me put here, electron neutrino, the guy who is interacting together with electron, and muon neutrino have similar interactions, so or practically the same. So the same type, the same Lorentz structure, the same strengths. So we deal with the correspondence. Electron, nu E, muon, nu mu. But then the question, are they still the same or different? So the question is nu E equals nu mu or not? That was the question. And already in the early days, there were some kind of indications that these are two different neutrinos. Because if nu E equals nu mu, you would expect the process like mu go to E gamma. So then you will observe decay of muon into electron and gamma. This decay still hasn't observed even now. So people are looking for this type of the decay, but it is not observed. Now the question, why? The point is that it's immediately existence of this decay under such conditions comes from the fact that we have usual muon decay. In usual muon decay, muon is transformed to electron and then emits two neutrinos, say nu E and nu mu. Let me put the errors in this way. Now, if electron and muon neutrino coincide, that we can close this loop. Have you started to study Feynman rules or not? Not yet. Anyway, so what may happen is that muon emits muon neutrino, and then muon neutrino, since it coincides with electron, is absorbed again, and you have electron in final state. Of course, such a decay cannot exist because of mass of muon differs from mass of the electron. However, you can emit photon here, and that process should exist. So this is precisely the diagram for this decay. In fact, Pentecourt was first who made the searches for this decay. He hasn't found this, and that convinced him that a muon neutrino and electron neutrino are different particles, because if they are different, you cannot make this connection, right? So what is the present limit? Let me mention, because experiments are continuing. And the present limit, and actually what people are putting bound on, is on branching ratio. What is branching ratio? This is ratio of decay rates, gamma, mu to E gamma, onto usual mode, which is actually dominates. So mu go to E and to neutrino. So this is usual. This is what we are looking for. And the present bound on this branching ratio is that it is smaller than 4.2 10 to the minus 13. It's suppressed by more than 12 orders of magnitude, at least, right? So, because we haven't observed this. And new series of the experiments, and the experiment which puts this limit is MEG in Switzerland. And MEG is essentially mu to E and gamma. So that's mu to E and gamma mag experiment in Paul-Scherrer Institute in Switzerland. And they want to improve this bound at least by 1 order of magnitude. And what is expected, at least in this series of experiments, that this limit will be improved to 4, 10 to the minus 14. Yeah?
Is this the precision that they ultimately have right now, or do they observe that event, but they are not sure?
No, they didn't observe events.
Not at all.
Not at all. And so they put the limit on this rate, so it should be smaller than this. Then you, during the time of observation, will not observe no one event. With certain confidence level, I don't know, this is, of course, one should provide confidence level. I think this is 90% confidence level. I can check. Okay? Now, of course, it's kind of difficult to make strong predictions, even if you assume this, because you have to compute this diagram. So you want to compute diagrams. Oh, please compute. Next, I will ask Takeshi to check what you will get. Okay? You are complaining that you are not struggling, or not facing this problem of computations. Okay, do this. I will see what you will get. Simple, right? This vertex or that one. Some divergence here you need to deal with. Because this diagram is divergent. So what you will meet when you start to integrate, even if you go to textbooks and find how the diagrams are computed, you will have some integral here, because you need to integrate over momentum of this particle in the loop, and that will be divergent. So what to do with this divergent integral? Unless you have consistent theory, and standard model is consistent theory and renormalizable, you need to cook something still, You need to make some kind of cutoff. And what you can do, you can make some cutoff at some energy, the highest energy which you have already explored by that time, say 1 GeV. And then you will get something like, for this branching ratio, 10 to the minus 3, 10 to the minus 4. I don't remember precisely. I made this estimation. Well, at least you can do estimation. So, and you will get now the bound which is 10 orders of magnitude stronger, which certainly indicates that that you cannot have this type of equality.
Are they searching for something new when they already have a stronger bound than the theory suggests? We have a
Yeah. So that is nice place where you can search for new physics. So now we know that in the standard model you can make precise computations. Again, I don't remember precisely. I think the branching ratio is something like 10 to the minus 36 in the standard model. And it is proportional, it's related to smallness of neutrino masses also. But however, if you have some new physics, then new physics can easily produce for you this decay at very high rates. So some new particles, actually, not neutrinos, but some other particles, heavy particles, can do this for you if you have Lepton number violation. Especially supersymmetric theories, they predict something which can produce this decay rate at very high, so at this decay at very high rate. And in fact, already these bounds strongly restricted so-called parameter space of the supersymmetric particles. So which means that they should be heavier than something, for instance. Or have some couplings which are smaller than something. Okay? So this is now the goal of this experiment is to search for new physics, not to check this difference. Now, Pontecorva has suggested experiment how to make these checks explicitly. That was not explicit, and then it was some uncertainty because you cannot make these computations. Who knows how to make a cutoff of this divergent diagram, and then the experimental bound that time was not so strong as now, and Bruno Pontecorva proposed the following way. He said, let's take pi and decay. Pion decay produces for you muon neutrino. And you know that it's mostly muon neutrino. Remember we discussed this, because the rate is proportional to the mass of charged lepton squared. This is crucial, right? Because otherwise you still produce in pion decay some amount of electron neutrinos. Therefore, you still have this background. So, you have muon neutrino from pion decay, and then you can explore how these neutrinos are interacting with neutron. So, standard process when you have proton and muon in final state. But if muon neutrino and electron neutrino are the same, then you would also expect that the final state with proton and electron, right? So this is if nu mu equals nu e, right? And so you would expect kind of equal number of events of this type of that time, if electron and muon neutrino coincide. So you expect Ne equals N mu. This idea has been realized soon after this. Melvin Schwartz developed an experimental technique to produce neutrino beams. So you need to produce neutrino beams, and quite intensive, because you still neutrinos are interacting quickly, and so you need to have beams of neutrinos. So Melvin Schwartz had the following suggestion, and this is how actually neutrino beams are produced in modern experiments too. So you have first accelerated protons which hit target and produce secondary particles. Among the secondary particles you have pions. Then you put focusing system here, the system of magnets. Which actually really focus your pions, because you have pions produced in different directions, and you want to have a neutrino beam which is directed in a certain way. You see, you cannot operate with neutrino beam. What you can operate with parents of, you can influence parents, but not children. So you do the following: put magnets and focus these pions. And not only this, you can select pions of certain electric charge, sign of electric charge, pi plus or pi minus, right? And then remove, say, pi minus if you want to have pi plus. And therefore, in this way, actually, you can select neutrino or anti-neutrino beam eventually. So after this focusing, which is called horns, and you can, the system of magnets, horns, you put direct your pions into decay tunnel, and this decay tunnel, its length depends on energy of neutrino you want to produce. So if you want to have high energy neutrinos, you want then produce high energy pions, and therefore decay rate becomes longer. And so the size of these decay tunnels from, say, 30, 50 meters up to kilometer lengths for the high energy neutrinos. But in the early days, I think it was 50 meters or something like this. Then what you do, so what happens here, pion decays here into muon and muon neutrino. So pion is still boosted, and therefore preferable direction exists for this. So you produce neutrino. Then after decay tunnel, you put absorption system or shielding system. to absorb all the particles but neutrinos. Electrons, muons, undecayed pions, etc. Of course, this is important. It's also important to absorb all the muons. So that's usually some plates of iron, but also some amount of just soil. So the detector of neutrinos is somewhere even in other experimental holes. So you have accelerator complex, and then you put your detector of neutrino, maybe 100 or several hundred meters far from the source, from the accelerator. And then finally you put the detector. This is actually a common scheme, of course, with some different details of practically all neutrino experiments which are performed nowadays. In the first experiments, the energy of neutrinos was about 1 GeV. The detector was spark chamber. So that what happens is that muon neutrino penetrate through all these kind of shielding systems, and then here it interacts with neutrons, giving muon or electron, and here is a recoil product. And then you detect this muon. And actually you will see the tracks of the gain of size of few meters of this muon marked by avalanches, by the sparks along the track. So again, the system works like you have some trigger here or some trigger, but in this case I think they have just continuous electric field. But you can use still trigger and turn it in certain moments. Especially since you have protons in bunches, they are not just continuous flux, so you should actually, you can get given information here when you expect this event, right? And then you have this pulse, electric pulse of high electric tension, and then you produce in this way avalanches along the ionization track. Now, a few words about the experiment. So, experiment was even repeated. First, it was in Brookhaven, and then at CERN. And the authors, which they get Nobel Prize eventually, Jacques Steinberger, actually, I saw Steinberger this year. I was at CERN in January, February, and I saw him. So he's still appearing. Of course, I don't know, he's more than 90, certainly. Then Malvin Schwartz. And Leon Lederman. The first experiment was in 1961 in Brookhaven in the US. And then it was repeated in next year in 1962 at CERN in Geneva. And during 8 months of operation, they have detected 56 muon events, and it was no excess of electrons, no excess above background. Of course, you have always some background. I don't know, maybe few as a background. No excess of E events, so, mu events, and no excess of E events. The conclusion was that muon neutrino certainly doesn't coincide with electron neutrino. You can wonder why Pontecorvo didn't got Nobel Prize. Also, it was his idea, a theoretical idea. See, he developed this, and he had even some experiments. He's an amazing person. He didn't got Nobel Prize. But you see, on his grave in Rome, people are saying it's written mu is not equal to nu e. So he was in the Soviet Union, he died in Soviet Union, but he has two graves. One is in Dubna and another one is in Italy because he's of Italian origin. I don't know if you know the story of Bruno Pontecorvo. If not, you can actually buy a CD. It was a movie created. It's an interesting story when he started with Fermi and then he immigrated to Canada. He was in Canada and then he disappeared from Canada and then appeared in Soviet Union, and he was in Dubna in Soviet Union all the time when he worked on many things. So what's interesting that Nobel Prize for this experiment was awarded even before Reines got a Nobel Prize. I told you this story. Now, to be more quantitative, you cannot exclude that this muon neutrino and electron neutrino are partially the same, or so-called wave functions overlap. And you can put a bound, nu e and nu mu, moduli square. And from this experiment, from this observation, you can find a bound something like 0.1. So, which means that muon and electron neutrino are different. But if they won't overlap, that should not be more than, say, 10%. This type of the experiments continued, and now the bound is around 10 to the minus 3.
I have a question about the Schwartz system design of the Schwartz. We produce neutrinos at the end, and we need to focus them, right?
No, we cannot do this, unfortunately. Yeah, we cannot do. So what you can do to focus, the only what you can do, you can have high energy pions. You can immediately estimate, maybe I will give you the problem, so it's good to have. So you have pion with energy, say few GeVs. Now pion has the mass 0.1 GeV, roughly speaking. And if you go to rest frame of pion, so it decays isotropically. So which means that perpendicular moment will be half of the mass of the pion. Therefore, neutrino beam which you are producing here has the spread, which is unavoidable, which is this 0.1, so even smaller, so 0.05 GeV, so 0.07 if you want, or 0.5. Actually, the energy of neutrino is even a bit smaller. Over the energy of pion. Suppose pion has the energy 2 GeVs. So this means that the angle is something like 0.02, 0.03. And it's unavoidable. So you have the beam which is expanding. Well, of course you have also detector which has some certain size. You don't need really to focus. But this is the problem for experiments when you have long baselines. Then the size of the beam becomes huge. It becomes, say, 100 meters or several hundred meters. And of course your detector is much smaller. You just look at some part of this neutrino beam.
So if we have something like a spreading problem, why do we put shielding with iron and soil?
Because we want to eliminate all other particles. Because you have muon produced here.
We don't want that.
I mean, we don't want this.
But
so this is the most.
In the muon decay, we have also electron neutrinos.
Yeah. So that's actually one of the backgrounds. However, if you remember, the muon has 2 orders of magnitude bigger decay rate. So which means that that your muons Some small part will still manage to decay and produce this background, but most of them will decay at much bigger distances. Those who will survive and not will be absorbed. Yeah, this background is taken into account. This one I'm saying, no excess of events. Some, I don't remember exactly, maybe 1, 2 events are due to background.
And the way we produce your neutrinos has less luminosity than what one can expect near a nuclear reactor. Or
Oh yeah, the fluxes are much smaller. Yeah, sure. So yeah, but what helps is that we are dealing here with higher energy neutrinos. Remember, neutrino is 1 GeV, which means that in reactors we have, say, 3 MeVs, which is 300 smaller. Then you square this, and you have 5 orders of magnitude bigger cross section. Though you will have smaller flux, of course, but you have much higher cross section, and this is the reason why we can still observe a number of events. But eventually, what is interesting, still appearance of electron neutrinos from new mu beam, so you create new beam. However, at very large distances, still you observe some electron neutrinos. And that has been observed. So, what does it mean? So, if you measure your muon neutrino flavor, what we are saying flavor, type of neutrino, close to production of new mu, there is no electron neutrinos appearing, which means that muon neutrino is different particle. However, if you let muon propagate quite a long time, you will observe electron neutrino and muon neutrino beam. Any idea how it happens?
Oscillation of neutrinos.
Yeah, right. So, and that has been observed. So what we have checked in the first experiment, that at least in the production point, new mu doesn't contain any admixture of electron neutrino. However, this admixture can develop due to oscillations. So I will discuss this in one of the final lectures of the course, the oscillations.
These oscillations means wave function overlapping is changing with time.
Yes, of course, neutrino, so there is a propagation and the wave function changes in the course of propagation. So electron neutrino is not produced in the beginning, but it is created during evolution of propagation of muon neutrino.
So this bound is only valid for production.
So this bound valid is somewhere here where you are close. At least, you know, at the production point you can say that a muon neutrino doesn't coincide with electron neutrino. Again, still that can be said with accuracy 10 to the minus 3 for time being. Still it is not excluded, and people are discussing this so-called breaking of unitarity these days. People are working on this, that maybe even at the production they are not completely orthogonal, what we are saying. So when this is 0, this refers to orthogonality. So these two states are orthogonal. But due to some reasons, if some new particle exists, heavy particles, it may happen that even with 0 baseline you have non-zero overlap. Okay?
Does the solution have anything to do with supersymmetry or
Which one?
to explain the non-orthogonality or?
No, again, what I'm saying, it is enough to say that some heavy neutrino exists, not usual light, very light neutrino, but heavy neutrino exists with masses bigger than, say, 30 GeVs or 40, 50 GeVs. Then existence of such neutrinos, even if you introduce this in standard model, can produce non-orthogonality. Let me discuss this later, because
A muon and electron can have that kind of oscillations.
this is common question, and the answer is yes. In principle, you can see these oscillations of so let me put in this way. What oscillate, at least in vacuum, are not mass states. Electron and muon are particles which have definite masses. They oscillate. So they cannot oscillate in vacuum. No, that's what at this point. But you can cook some composite state made of electron and muon. That state will oscillate. But not electron. If you produce electron and it propagates, it doesn't oscillate. In contrast to electron neutrino, which do oscillate, because electron neutrino has no definite mass. It has mixture of states with different masses. So now why people got this Nobel Prize? Why this extremely important discovery? Now let me, in the final 10 minutes, discuss implications of this discovery. So this is important. When you discover something, find something, think what is the meaning of, because there were a number of situations or cases in particle physics when people have found something but didn't discuss, didn't stress this, and then lose. Gross and Wilczek got a Nobel Prize because they made some computations of, say, one-loop diagrams and then established that the sign is different from what was expected before, and then they said, oh, this is important, this is asymptotic freedom. It was another guy, he's still alive, in Soviet Union. He did the same computations. He has found the same sign, just published paper, the same sign, without any, and he didn't got Nobel Prize, you know. So, do something, and this is quite simple, but then you need really to think what are consequences. So what are the consequences of this? First, this experiment essentially considered as discovery of muon neutrino. Why? Remember we discussed criteria. Because we produce muon neutrino in one place, then this muon neutrino propagated, and then it interacted in our detector, producing muon, which means transferring energy, transferring momentum and quantum numbers. So that was criteria to show that what you are producing is a real particle, not some phantom or some dynamical crazy thing. So that was considered as discovery of muon neutrino. Second, now the doublet structure of weak interactions emerges, because we can put nu E and E and consider them as doublet, and they form current, and nu mu and mu. They form another charge current. And this is what appears in the standard model, eventually. So the particles interact in pairs. And what happens is, and people check this, that with electron we always have electron neutrino, not only in this process, but in all other processes. People study it, and what neutrino state which appears with electron or interacts with electron or produces electron is always electron neutrino. The same story is with muon. The neutrino state which interacts with muon or produces muon or is produced by muon is muon neutrino. So how to describe this? To describe this, we introduce lepton numbers, even 2 lepton numbers. Which are conserved in weak interactions, and other also. And electromagnetic and strong interactions. So we do the following: we introduce electron lepton number and a muon lepton number for nu E, nu mu, and mu, we use the following prescription. 1, 1 here, 0, 0. For muon, vice versa, 0s here and 1 here. And for antiparticles, for antineutrino, for positron, the charges are opposite. So L nu go to minus L anti. And then in all interactions, weak interactions, strong interactions, electromagnetic interactions, total lepton number are conserved. Total, I mean separately total electron number and total muon number are conserved. So for instance, in pi decay, when we have, say, pi plus, mu plus, and then nu mu, we have what? For electron lepton number, everything is trivial, everything is 0. And for L mu, we have 0 here, we have minus 1 here and plus 1 here. So 0 also in final state. Yeah?
It's valid for all electromagnetic and weak interactions, right? We can always distinguish.
And strong interactions.
And strong interactions. We always distinguish what caused, for example, some kind of a process, if it is by electron or muon or.
Yes, yeah.
But do the neutrino oscillations violate this?
Yes. And neutrino oscillations violate this. And this is related to the interactions which produce masses of neutrinos. If you want, these are Yukawa interactions. We still don't know exactly the mechanism of neutrino mass generation. I will discuss this later. But those are the interactions, and partially it can be due to interactions with Higgs boson. Some people say, okay, that probably also weak interactions, but it is even weaker or super weak interactions if you want. I refer to weak interactions as those interactions which are due to exchange of W and Z bosons. In this sense, they are conserving lepton number. What breaks lepton number is interaction responsible for mass of neutrino.
So then our construction, pair construction is somehow mixed into each other in that case. Like if we have at first electron neutrino,
Yes.
muon neutrino,
Yeah.
those pairs are somehow interacting with each other.
Well, what actually, if you want, what breaks is vacuum, because masses are produced by non-zero, so non-trivial vacuum state, and when neutrino propagates in vacuum, physical vacuum, so that leads to this transition from electron to muon neutrino. Yes.
At this time, there was discovered the quarks and the flavites of the quarks also.
Yes.
So, is there something relating to that to start to search for the tau particle
To search for what?
for the tau?
For tau.
Tau.
Yes. No. For time being, again, we will come to discovery of tau. I'm following kind of historical way. Then you understand how things develop. Yes. What do you want to know about the tau? Tau should also be included in all the scheme, and we will discuss this. And there's a mixing also tau neutrino and oscillations of tau neutrino.
Because existing of only electron and muon, I don't know, but if we look at it as SU2 group, it will not be, the symmetry will not be complete.
Why? Well, we can easily, so that eventually forms the SU2 doublet. At least that's okay. Or SU2 cross U1, if you want to explain it. But don't rush. I mean, ask questions about what we are discussing now. I will come to all this story with mixing. The fourth important implication is lepton mixing. Soon after discovery of muon neutrino, Maki, Nakagawa, and Sakata There's also Sakita, that is Sakata. What they said, that maybe electron and muon neutrinos are not the states with definite masses. So they had some model of hadrons. And they kind of included these leptons and discovered neutrino into their scheme. And I say maybe electron neutrino actually is mixture of two other states which have definite masses. So nu1 and nu2 have definite masses. And muon neutrino is orthogonal combination. So it's cosine theta nu2 minus sine theta nu1. So you can easily check that nu e matrix element and nu mu is 0 in this case if the states nu1 and nu2 are orthogonal. And the states nu1 and nu2 have definite masses. Nu1 and nu2, that has mass m1 and that has mass m2. Okay? So if you would construct spectrometers, this is Gedanken experiment, you say have electron neutrino and then use mass spectrometer to see what is the mass of this electron neutrino, you would see two peaks, which corresponds to nu1 and nu2. Not only this, they said that the mixing leads to transmutations. They call these transmutations of one neutrino into another. In the course of propagation, so that nu mu can go to nu e. And this is the same with oscillations. And actually oscillations have been introduced before in 1957, again by Bruno Pontecorvo. But he was talking about nu to nu bar oscillations. This is what we refer to flavor oscillations, and Pontecorvo proposed neutrino, anti-neutrino oscillations. And let me say, just a final point, eventually discovery of muon neutrino led to introduction of charm quark. So that will be what is inspired. That we will discuss after we will discuss quarks. We will start this next lecture. And the point was that it was kind of asymmetry. There were 3 quarks and then 4 leptons. And then Glesho and Bjorken said, okay, this is not nice. It's nice to have something symmetric. And so probably another quark is the fourth one, not charm quark. So this is the way how charm quark for the first time appeared in physics. Okay, questions?
This lepton mixing is not contradictory with lepton number conservation, right?
No, that's already a signature of lepton number conservation. Because this type of mixing implies mass term of the following type, nu mu and nu e plus Hermitian conjugation. So that actually implies non-conservation of lepton numbers. So you can get this when nu1 and nu2 have definite masses, provided that you introduce this so-called non-diagonal mass term, which explicitly violates lepton number.
So we actually have lepton number conservation in this case.
What do you mean we have?
If it is not valid under this.
Well, if you consider the processes which are not involved neutrino masses, then you have lepton number conservation.
Have that term.
Well, again, if you have some processes for which you can neglect this term, then you have lepton number conservation.
Or maybe we could do the lepton number conservation not for electron and muon neutrino, but 1 and 2 neutrino that we have.
But for
The new types of neutrino that we introduced. Maybe they
what are new types?
V1 and Nu1 and Nu2.
No, U1 and U2, what is interesting, you can, so to avoid confusion, again, we will discuss oscillations later. So you can use this and you can express Nu1 and Nu2 in terms of Nu mu and Nu e, right? So you can invert this equation. And now you know that Nu1 and Nu2 have masses, so you have in your Lagrangian term like Nu1, M1, Nu1, Nu1, plus M2, Nu2, Nu2, right? So that's, you need to have such a mass terms. And when you insert here this Nu1 as combinations of Nu mu, then you will get immediately all these lepton number violated terms.
In both cases, it's violated.
What are
That's on them. I was trying to say that if we introduced a lepton number, a new lepton number based on Nu1 and Nu2, maybe they.
No, well, you see, I don't know what is the sense to introduce another. You can introduce say L1 and L2 if you want. Then it will be violated in the interactions.
Because we again have those kinds.
Because you will produce in the same process, you will produce both Nu1 and Nu2. Sorry. So, do they deserve Nobel Prize? No. Just so many consequences, right? So, and it's amazing, you know. I was always, I don't know if you appreciate it or not. I was always curious how the discovery is made, you know. So how people came to this. Right? That's interesting. I was always trying to figure out what was history, how people managed. I mean, very often it's kind of accidental or it's simple, unexpected, and eventually simple, right? So till now we already discussed a number of maybe 10 different discoveries awarded by Nobel Prize. Right? That's very simple. What is not simple? What was not simple? Tell me. Logic. I was curious. What is the logic? How people came to some. This is Lance's progress breakthrough.
And you say that Dr. Nobel Prize before Ryan's experiment.
Yeah.
Before.
Not before Ryan has got a Nobel Prize.
Not Nobel Prize. But people were confident about the existence of neutrinos at that time, right?
Yeah, I remember. I told you nobody knows actually what is. Well, probably because it is. It should be 25 years, I think, after award. So Ryan has got Nobel Prize in 95, which means that in 2000, in 2 years, a Nobel Prize committee should open box and to say why, and then it should be somewhere stated why he got Nobel Prize so late. But I told you that one of the things was that he first made a statement on the basis on wrong theoretical computations, and this is what people are saying.
Yes,
yeah. So, which means that one of the criteria, agreement with what is expected, was not satisfied, right? So then it was new computation, and then the results were not in coincidence with correct computations, which is bad sign, right? But then he corrected his experimental results. So, I don't know, of course, details of this story, but that could affect, of course, decision of Nobel Prize committee. Okay? Then on Monday, right? So, one remark. So in these exercises, there is exercise when there are two scatterers, right? And you need to evaluate what is the energy of primary particle. What was not said that it is assumed that scattered wave has the same energy, so the scatterers are very heavy, and therefore the secondary waves which are emitted by scatterers, they have the same energy as original one. Okay. Okay. So see you on Monday. Oh, so maybe we'll discuss on Monday because I'm too busy today. Thank you.